Okay, today we're going to start on chapter 13.1. Okay, but we have some preamble first on chapter 13 itself. So we have done coordinate geometry in the past, so we know that we talk about gradients and all. So in differentiation also, we always get the gradient of the function. We get the gradient function itself to tell us what is the gradient at different points of the graph itself. So today we're going to relate and marry these two concepts, right, from coordinate geometry, where we deal with the gradient of straight lines and all, with the gradients that we can actually find right from the graph itself. Then later on in this chapter, we talk about rates of change. So what are rates of change? So basically, right, we talk about how two variables change, right, in relation to each other. So like for example, speed. Okay, speed is meter per second. So what is the change in distance per second? So that in essence, right, is a rate of change. So we'll deal with those later on in the chapter, but first, okay, today we're just going to deal with tangents and normals. Okay, so today in 13.1, we'll learn to apply differentiation to gradients, tangents, and normals itself. Okay, so now, without much further ado, we will look at example 1. Okay, just a quick recap, right? What is a tangent? So if you look right at P, okay, the tangent at P itself. So tangent is at this point P, 1, 2. Okay, we have it touches, this straight line touches the graph at exactly one point. It touches there exactly. This is known as a tangent at P. Then now we also have the normal at Q. What is a normal at Q? So at Q itself, okay, there will be a tangent like this. Okay, so at the tangent, at this point Q itself, if you draw a perpendicular line like this, okay, what you get, right, is 90 degrees here, this perpendicular, so 90, of course. So the normal, right, is perpendicular to the tangent. I repeat myself, the normal is the line that is perpendicular to the tangent. And if you recall from coordinate geometry, how are they related? The product of their gradients will be equals to -1 for perpendicular lines. Okay, so these are the essential information that we'll need to understand and try to solve, right, these questions today. So now let's begin. So to find the tangent at P, so this is the equation of this curve itself, x squared minus 4x plus 5. If we differentiate that, okay, what we get is 2x minus 4. So at P, my x value equals to 1. Very simple. So x equals to 1, I just substitute in. I find that the gradient of the tangent at P is equals to -2, which I have written it down over here. Now, if I apply, okay, y minus y1 over x minus x1 is equals to the gradient. In this case, the gradient is -2. All right, I can find the equation of my tangent at P itself. So if you just solve this very quickly, you will get y equals to -2x plus 4. For part 2, the normal at Q, be very careful. Okay, once again, we have this from the previous part itself. So from the previous part, right, this is the gradient function. So at Q, my x value is equals to 4. So I substitute that in. I get the this gradient is equals to 4. Be very careful. This gradient of 4 is not, okay, the gradient of the normal. This 4 refers to the gradient of the tangent. So this tangent line here, the gradient is equals to 4, but the gradient of normal, okay, so it's 4 times m, okay, gradient of the normal equals to -1. So m, okay, equals to -1/4. Hence, if you look at my statement, gradient of normal at Q is -1/4. Okay, so be very careful here. This is a common misconception. Then I have the coordinates 4 and 5. I have the gradient of the normal is -1/4. So I apply y minus y1, x minus x1 is equals to the gradient. As you can see over here, simplifying, you get the gradient of the normal is y equals to -x plus 9. Okay, now the last part, part 3, they want the normal at the point where the curve crosses the y-axis. Okay, at the y-axis, what I do know is that my x value is equals to 0. So given that my curve is y equals to x squared minus 4x plus 5. I sub x equals to 0. So y equals 0 square minus 4 times 0 plus 5. My y value is equals to 5. So at the y-axis itself, I use the value of x equals to 0. I found that my y value is 5, which I have labeled over here. Then to find the gradient of my tangent, again, I'll be very careful. Gradient of the tangent when x equals to 0, okay, you sub it in, all right, into 2x minus 4, which we had from the earlier parts, okay, which was dy dx. When x equals to 0, as I have shown here, you will get 2 times 0 minus 4 is equals to negative 4. So if my gradient of my tangent at this point, this tangent, the gradient is negative 4. So negative 4 times m, m being the gradient of the normal, I get my gradient of my normal to be 1/4. So if I substitute that in, okay, y minus y1, x minus x1 equals to m, I find that my gradient of my normal at the y-axis is 4y equals to x plus 20. Okay, I invite you now to try one, and then I will give you the answers shortly. So please pause the video and actually try this question. And I will move in 3, 2, 1, let's go. Okay, for try one, first thing we are trying to find the gradient, okay, of the tangent at A. So first we find the gradient function, 3x squared plus 6. So at A, my x value equals to 2. So here, x equals to 2. I find that the gradient of my tangent is 18. So this answer does it a bit differently, but never mind. I can show you what I will have done. Y minus 15, x minus 2 is equals to 18. You solve it, okay, or you rearrange the algebra, okay. Then you get y equals to 18x minus 21. Okay, for part 2, we're dealing with a normal, okay, so not a tangent, now it's a normal. So the same thing, we have the gradient function, dy dx is equals to 3x squared plus 6. So at b, the x value is negative 1. I put it into this gradient function. I find that the gradient of my tangent at b is equals to 9. So at b, down here b, the gradient of my tangent is equals to 9. But that's not what we want. What we want is the gradient of the normal. So if I want to find the gradient of normal, m times 9 is negative 1. So m is negative 1, 9. So gradient of normal is negative 1 over 9. Then what we can do here is, again, we can apply y minus negative 12, x minus negative 1 equals to negative 1 over 9. Then if you solve it, okay, you resolve it, you should get this. Y equals to negative 1 over 9x minus 109 over 9. Okay, for part 3, they ask for the normal at the point where the curve intersects the y-axis. So the y-axis, once again, my x value equals to 0. So actually we are looking at this point here. So my x value equals to 0. You substitute this into the curve itself. You will find that your y value is negative 5. So this point here is 0, negative 5. Now, here we have the gradient function which we have obtained earlier is 3x squared plus 6. So if I use my x value to be equals to 0, the gradient of the tangent, okay, at this point is equals to 6. But what we want is the gradient of the normal. So I take negative 1 divided by 6, I get negative 1 over 6. Same thing, we apply y minus y1 over x minus x1 is negative 1 over 6. You resolve it, you will get this what I call equation of the normal at the point where the curve intersects the y-axis. Okay, we now move on to example 2. So example 2 shows the diagram shows part of the curve y equals to x squared minus 3x plus 2. And the tangent at the curve is point AB. Okay, so now the tangent, okay, is perpendicular. So which tangent we're talking about? This tangent is perpendicular to this line. So how are they related? It means that their gradients, the product of their gradients will be equals to -1. So never mind. First, what I'll do here is this. I will take this y equals to x squared minus 3x plus 2. I differentiate it. So I get 2x minus 3. Then what I do here is this. For this line itself, okay, I rearrange the equation. So 2y equals to -x plus 6 over here. Then I divide by 2, y equals to -half x plus 3. What I'm doing here is to obtain the general equation of the line, y equals to mx plus c, so that I can read, okay, off the equation itself the gradient of the line. So for this green line over here, okay, I've seen that the gradient is -half. So if this is -half times m being the gradient of this blue line, okay, equals to -1, because it is said in the question that they are perpendicular. So I find that the gradient of this blue line equals to 2. Okay, then I know that for this graph itself, okay, the gradient along all the points is 2x minus 3. So what I'm saying is, I know that at this point, my gradient is equals to 2. So I equate it, right, to the gradient itself. So 2x minus 3 is equals to 2. I solve. I will find that at this point, my x value is 2.5. So the x value corresponds to a. So a is 2.5. To find my y value, I use the equation of the curve itself. I substitute in because the equation of the curve will relate x and y. So I will get my y value to be 3/4. And this y value corresponds to the b over here. So b is 3/4. Now, for part 2, it's a simple one. I already know the coordinates of P is 2.5 and 3/4. I know the gradient of the tangent is equals to 2 from part 1 itself. I just use y minus y1, x minus x1 is equals to gradient 2. I resolve it. I get the equation of the tangent at P itself. Okay. Please pause the video, okay, and try 2 now. So there's this tangent of the curve to the curve, okay, and at the point Q is perpendicular to the line. Okay, quite simply, if you just start here, okay, you get y equals to -1 over 6x plus 1. So the gradient of this line is -1, 6, and then is perpendicular to the tangent. So I think that helps a lot already. You should be able to get that the tangent gradient is 6 itself. But I will just pause here and let you try it out. And once you're ready, you can unpause, and then we can actually try out our explain this question in 3, 2, 1. Okay, first and foremost, the graph is given by ax plus b cubed. So at 0, 8, actually this one is a simple one. We can substitute the x value to be 0 down here. This eliminates the a itself. So we can actually solve for b. The b value is 2. So what I get is that I can fill in the value of b, ax plus 2 cubed. Then now, if I differentiate, this differentiation may be a bit tricky. Let me help you here. I start from here. So it's ax plus 2, the 3. I bring it down. 3 minus 1 gives me 2. You differentiate this. You differentiate ax. A is a constant. That's why you get a plus 2. 2 is, you differentiate, you get 0. That's why this becomes 3a ax plus 2 squared as given here. So now, the gradient of the tangent at this point there, okay, at 0, 8. So when you substitute dy dx when x equals to 0, so here is 0, you get 2 squared is 4, 4 times 3 is 12a. Earlier, I've already spoken about how, okay, I know that the gradient of that line, which is perpendicular to this tangent, is -1, 6. Hence, by m1 times m2 equals to -1, I now know that the gradient of my tangent is equals to 6. And since the gradient function is 12a, I equate 12a to 6. I solve for a equals to half and my b value is equals to 2. And this concludes this subtopic. Thank you for watching.